Alright, dudes, chemistry. So today we're going to talk about alkanes to alkenes, how we get there, and in particular, ethane to ethylene. Remember, ethene and ethylene are the same thing. We're going to use the name ethylene because it's cool. So today we're going to look at these two ideas here. We want to be able to identify the sources for industry of ethylene, and particularly from the cracking of some fractions of the refining of petroleum. We also remember fraction is a certain amount of the crude oil that comes out of the ground. We also want to identify that ethylene, because of the high reactivity of its double bond, is super duper useful and can be transformed into many useful products. So what's the point? You should be able to identify that ethylene and ethene and ethylene are the same. You should be able to do that. You want to explain the reactivity of ethane compared to ethylene and the properties of alkanes and alkenes. So we're using ethylene and ethane as our model for the entire setup. And you want to be able to explain the cracking of ethane to ethylene, which is also super interesting. So we've looked at burning that. Now we have another use for fossil fuels. We use fossil fuels for much more than burning. Rubbers, fertilizers, synthetic textiles, so polyester, plastics, pharmaceuticals. Basically, ethylene is an extremely useful chemical, in particular for both PVC, polyethylene, lots of solvents in industry, brake fluid, radiator coolant, paints, cosmetics, toothpaste, detergents, and a bunch of other things as well. However, it's not the easiest to deal with. It is a lung irritant, and we produce it from ethane found in petroleum gas. Now, yes, ethylene is distilled out of petroleum gas as well, but it's not nearly as common as we need it to be. So we can go from ethane, which is this, into ethylene plus hydrogen. All right. So before we get further into that, let's look at alkanes and alkenes. Here we have ethane, and here we have ethene or ethylene. Hydrocarbons of ethane and ethane, they're simple equivalent alkenes and alkanes. In other words, they have the same number of carbons. There's similarities. They've got some. They both have low melting points and boiling points, very low melting points and boiling points. They're both non-polar and have weak dispersion forces. They are relatively insoluble, and this means in water. And it burns. So if we burn ethane here in oxygen, we get, if we have 2 particles of ethane, we'll end up with 4 of carbon dioxide and 6 of water. If we burn ethylene, we need less oxygen, and we'll end up with pretty much the same amount of CO2 and less water. So if we double this to make that 2 at the front, we end up with 6. So we've got less oxygen, so it's easier to burn. We'll end up with 4 carbon dioxides and 4 waters, which is less water pollution, which is actually a thing, by the way, when the water enters the atmosphere. So what are the differences? Reactivity. Ethene, due to its double bond, is much, much more reactive. And this is the reason ethylene is used in industry so extensively. We can pretty much make the polymers that we're going to talk about out of ethane if we needed to, but it's much, much harder. It's very much easier to make it out of ethylene. Make the ethylene first and then make it. So let's have a look at the reactivity of them. Alkanes undergo substitution reactions. What does this mean? So you know this by now. So if an alkane undergoes substitution reactions, it means a hydrogen is substituted out. So let's have a look here. So an ethane undergoes a breakdown and substitution in the presence of UV light with bromine water. So we're in bromine water here. We'll do this in the classroom. You add bromine water to it in UV light, which means you need to supply energy. It goes through a substitution. You get hydrogen bromide and 1-bromo ethane. Now, alkenes, on the other hand, they go through addition reactions. So substitution reactions, addition reactions. Now, what does this mean? So the double bonds are broken down and the other atoms are added in. So here, if we've got ethene with hydrogen gas, the hydrogenation of it, we just get ethane. It's that simple. If we add it to bromine water, we end up with ethylene and bromine water. It gives us 1,2-dibromoethane. And this is colorless. And this is actually one of the ways we can test what we've got. So we can use this as a test to see if we have ethane or sorry, an alkane. And an alkene is the addition of bromine water. And in the presence of an alkene, or an alkyne for that matter, it will go colorless. And that's a really important test, and we'll do that in class. So let's look at the thermal cracking of ethane, or ethane to ethylene. Over here we can see that it is an endothermic reaction, and energy is given what? Yes, it's an endothermic reaction, so energy is absorbed in. This delta H is positive because that means it is holding extra energy inside the bonds. So we can crack ethane, which is an abundant natural gas. In particular, the Cooper Basin, which is this big area here, and it supplies about the majority of Australia's liquid natural gas, and is 9% ethane. And unfortunately, there's also a big water table that lives there as well, and we'll get to that later on. So it's cracked at 850 degrees to produce both ethylene and hydrogen gas. It is then cooled rapidly to prevent ethane from reforming, and then when the ethane's reformed, decomposition into solid carbon, because that would be bad. We don't want that. It's endothermic, therefore the higher the heat, the higher the yields. All right. We'll have a look at that in a bit more detail in class, and in particular we're going to look at detecting if we have an ethane or an ethene present. See you then.